All right, you guys, this is our week 7 wrap-up video. And this is a lot about the acids and bases and hydronium ion concentrations, titrations, buffers. So let's take a look. So someone made a comment that I thought that if a solution has more than, and this is just exactly quoted, it could be acidic or basic, but a solution with this 1.7 times 10 to the negative 8 can be considered acidic. So that was just one of the comments, and I just wanted to clear up some things in there, and that came out through that comment. First of all, you have to be specific about that 1.0 times 10 to the minus 7th, what that is referring to, right? And usually from that section, it's usually going to refer to the concentration of H plus or H3O plus. Remember, those are interchangeable. So hydrogen ion or hydronium ion. And we represent the concentration with these square brackets, okay? And we put the H plus in there. Or are we talking about the concentration of OH minus hydroxide ion? And again, with the square brackets, it means concentration of. And so we said that, with water, and when it self-ionizes, that they're equal, right? So you end up, if it's completely equal, your H plus and OH minus concentrations are exactly 1.0 times 10 to the minus 7 each, okay? So therefore, if your H plus concentration ends up being greater than that, that means you have more H plus than OH minus, more hydronium ion than hydroxide ion. That means that there's something in there giving off a lot of protons. And from my last wrap-up video, I know we talked about something that gives off protons, that H plus, that hydrogen ion. That's something that's an acid. So if we have a concentration that's greater than this times 10 to the 7th, that means that H plus concentration is something like this. And I only put this as an example because I want you to realize that these are negative numbers. So that this number, this is actually bigger, right, than this number. And if you wrote out the actual full number, you would see that this is, point and then 5 zeros and then 1. And this number, the times to 7, is a decimal point and then 6 zeros and 1. So 1 times 1.0 times 10 to the minus 6 is actually bigger. And if that's true, it's acidic, okay? And again, this could be various numbers. This is just an example. The point is, if it's greater than 1.0 times 10 to the minus 7th, then it is acidic, okay? Now, if that H plus concentration is less than that, meaning there's not so much acidic component, again, an example is something like, again, it's kind of weird to think of it, but less than would actually be a greater negative number than the solution's basic. And again, we can do the same kind of reasoning with our hydroxide ion concentration. So again, remember the kind of middle point is this 1.0 times 10 to the minus 7. So if our hydroxide ion is greater than that, that means there's more. And again, that would look like a number like this. And that means it would be basic. If our hydroxide ion concentration was less than, and again, that's an example here, then it would be acidic. Okay, so let's take a look at some of the questions you guys were asking about in the discussion section. Okay, so, sorry, let me adjust my Zoom bars. Okay, so one of them was a solution has a hydroxide ion concentration that is 1.7 times 10 to the minus 8. Is it neutral, basic, or acidic? Okay, so again, I put these here from the previous slide, but you can reason it out. You don't have to memorize this. I don't recommend memorizing this, okay? What I recommend doing is remember that 10 to the minus 7 is that middle point, okay? I look at this and I see, okay, well, this is 10 to the minus 8. This is less than that, okay? And we're talking about hydroxide ion concentration. So if the hydroxide ion is less than our middle point, that means the rest of it is H plus. And if there's a lot of H plus hydrogen ion, right, that hydronium ion, then that means that the solution's acidic, okay? That's what an acid is. Okay. So again, please email me if you have any further questions or about this, okay? All right, which of the following represents the equilibrium chemical equation for the partial ionization of the weak acid? Okay, so again, this one, all I was seeing is like, I want you to answer this question. All you need to know is the definition of an acid that says that acids give up protons. Okay, I already told you it's a weak acid. I told you we're doing this partial ionization. So let's take a look at the equation and don't get overwhelmed by it. You know, take a breath in through your nose and just look at it. What do you see, right? We see HFAQ. So we have this this weak acid, which I told you in the question, it's in an aqueous phase, plus H2O. Okay, it's with water. That's the definition of aqueous. That's a liquid. And when it reacts, we end up with this F minus. So what happened in going from left to right, right? We went from HF to F minus. So it lost a proton, or it gave up a proton, and the water accepted it. So that looks pretty much like our definition of a weak acid, but let's just check the second one just to be sure. This is our HF, again, reacting with water, H2O. After the reacts, you can see now it's H2F plus. So it gained a hydrogen. And so now that was our definition of a base. So it couldn't be the second one, okay? So it couldn't be the second one. It has to be that first one. Okay. All right. Now this can be a little tricky. This is again, this has a lot to do with math. So this one is, a solution is known to have a pH of 4.57. What is the hydronium ion concentration of the solution? So we have this equation, pH equals the negative log of our H plus concentration. Remember, H plus and H3O plus are interchangeable. So this could also be H3O plus. The equation gave me the pH. So I plugged that 4.57 in for pH, and it's asking me for this hydronium ion concentration. It's asking me for the H plus. So this is always a little tricky step in getting from this second bullet point to this third bullet point. So if you didn't know, log is like a logarithmic function, and it's to a base of 10. So to kind of isolate H plus, the algebraic manipulation you would do is you raise the other side to the power of 10. And we also take that negative sign, and it also transfers over here. So we end up, so by taking 10 to the negative 4.57, we get rid of that minus log, and we're left with our H plus concentration. Okay, so make sure you know how to plug this into your calculator. Please do this calculation on the calculator you will be using to take tests, and see, do you get this answer? So 10 to the negative 4.57 equals 2.69 times 10 to the minus 5, and this is molar, and then that's our hydronium ion concentration. Okay, so again, the tricky point here is going from that second bullet point to that third bullet point, and knowing that to kind of get rid of a log, you take 10 to the, okay? All right. So then titrations, oh man. So this was one of the problems on the titration section. And in office hours, I was working with someone that, God, I just wish we had like some steps. And so these are kind of the really rough steps we came up with in office hours. And I thought it'd be nice to share them with everyone. And so maybe it will help you with a titration problem. Pictures also help. I didn't do that in this video. I'm not going to draw a picture, but if you draw a picture of the beaker, and the Erlenmeyer flask is really the proper one, and the burette, and kind of where's the acid, where's the base, what's the concentration, sometimes it helps people visualize that. And there's a great video on the Top Hat page. Okay, so let's go through these steps, and then I'll go through this problem. So we said first we got to do it. We have to come up with a balanced chemical equation. Oh, wait. A little bit of warning. A lot of times people teach this using the dilution equation. So C1V1 equals C2V2, or M1V1 equals M2V2. And I've been told, you might find it on the internet, you might hear it from another tutor. It works if all the coefficients in your balanced chemical equation are 1, okay? If it is not 1, that equation does not work. I will give you a test on your exam that does not have a 1-to-1 ratio, okay? Because you gotta, again, if you understand what you're doing, then you can think through this, okay? So whenever you're doing a titration, you should always start with the balanced chemical equation. You should convert any volumes to liters. The third step is you wanna find the moles of the reactant that you have the molarity and volume for, okay? Then you want to convert the moles of that reactant. You want to convert to the moles of the reactant for which you're trying to find the molarity of. And for that, you will need the balanced chemical equation you came up with in step 1. And then you're going to find the molarity of that reactant by dividing by the number of dividing the number of moles by the volume in liters. Okay, so let's walk through this. Let's look at this question. So it's a 20 ml sample of clear fluid is removed from a patient's stomach and analyzed for hydrochloric acid, so HCl, by titration. A 0.100 molar sodium hydroxide solution is used as the titrant, okay? In the titration, 2.37 milliliters of the base is needed to neutralize all the acid in the sample. What is the molarity of the hydrochloric acid in the stomach fluid? So I always wonder, sometimes I don't know, but hopefully you guys are recognizing that sodium hydroxide is a base. So down here, when it says 2.37 mils of the base is needed, they're referring to the sodium hydroxide, okay? So again, we're analyzing for hydrochloric acid, we're doing a titration, we're using sodium hydroxide as the base. So we got to come up with a balanced chemical equation between sodium hydroxide and hydrochloric acid. So here it is, NaOH plus HCl. And remember, acid plus base always gives you water and the corresponding salt. You can look, this is a balanced equation. This is a 1:1:1:1 ratio. So using that M1V1 equals M2V2 would work here. However, I don't recommend it as your instructor, because like I said on your test, I will not do that. Okay, so number 2, we're going to convert all our volumes to liters. Okay, so we took our 20 milliliters, and that's of our HCl, and convert that to 0.0200 liters. And then the 2.37 milliliters of our base becomes 0.00237 liters. Okay, so that was of the NaOH, the sodium hydroxide. Okay, 3, we're going to find the moles of the reactant that you have the molarity and volume for. Okay, so like for the hydrochloric acid, I know the volume's 20 mils, but I don't know the concentration. That's what it's asking for. It says, what is the molarity? That's concentration of the hydrochloric acid. That's what we're trying to find. Okay, and remember, molarity is moles over liters. So we have the liters, okay, right here, but we don't have the moles, and that's what we're trying to get to. But first, we got to find the moles of what we do have the molarity and volume for, and that would be our sodium hydroxide. Okay, so we know it's 0.100 molar, and we know we have 0.00237 liters of it. Okay, and so the moles of the sodium hydroxide I can find by just multiplying those two. Remember, capital M is molarity, that's moles over liters. So when you multiply, liters will cancel and you end up with moles. So you end up with 0.000237 moles NaOH, sodium hydroxide. So the 4th step is you want to convert to the moles of the reactant for which we are trying to find the molarity for. So we're trying to find the molarity of HCl. In the previous step, we found the moles of NaOH. Now we want the moles of HCl. This is where the balanced chemical equation comes in. We got to go back to the equation we came up with in step 1. And we see it's a 1:1 ratio, okay? Now, I always like to do sulfuric acid, okay, where it's like a 2:1 ratio or a 1:2 ratio, okay? And so, but in this case, it's a 1:1. So it's not going to change our number of moles, but it converts it from moles of NaOH to moles of HCl, okay? And like I said, again, if it's not 1:1, then the number will change. But because it's 1:1 here, the number does stay the same. But look at the units. Units are so important. So our 0.000237 moles sodium hydroxide times this fraction, moles of NaOH cancel. We're left with moles of HCl, and it just ends up being 0.000237 moles HCl. Okay? And then the last step, to find the molarity of the reactant by dividing the number of moles we just found in the previous step by the volume in liters. So there's our moles of HCl from step 4. There's our volume in liters from step 2. And if we divide those, we end up with 0.01185 molar HCl. Okay, So there's kind of some steps to help guide you through titration problems. Try it out with a sulfuric acid problem. I believe there's one in the homework. And come see me in office hours or send me an email letting me know how it went for you. All right, there was a couple more things. You guys were asking about buffers in this section. So we define buffer as a weak acid plus a salt derived from that weak acid, or a weak base plus a salt of that weak base, okay? And the reason for people going into the health fields why buffers is so important is because in a person, it's so important to maintain the pH of the blood. And your blood has a bicarbonate buffer system going on. And so that helps to, again, it helps maintain this dynamic steady state, right? Homeostasis in the body, okay? So whenever you're trying to identify if something's a buffer or not, first you got to figure out, is it a weak acid or a weak base, okay? So in this case, I give you this, okay? I give you these two. This has a metal, the sodium, okay? And in this case, it's sodium ion. So this is going to be the salt. So we got to check this out to see if it's the weak acid. You should memorize those strong acids. This is in the form where it's got this proton out here that kind of gives you a clue that it is an acid, and it's not on your strong acid list. Therefore, you can deduce that it is a weak acid. And the way you figure out if it's a salt derived from that weak acid is you just take that weak acid, remove the proton, okay? And then that leaves you with this CHO, CHO2 left. But you always need a counter ion because that would be CHO2 minus. That would be an anion, and you can't just find an anion sitting on a shelf in a chemistry stockroom. You need the counter ion, and in this case, it happens to be sodium. So sodium, potassium are really common counter cations, okay? So we get NaCHO2. So this is the salt of this weak acid. So therefore, this is a buffer, okay? This one I kind of just gave it away right away because I expect that you look at this and see HCl and you're like, strong acid. HCl, strong acid. That should be a correlation you're making. And you're like, okay, HCl is a strong acid. It cannot be a buffer. It's, yeah. Okay, so some oxidation reduction reactions, okay? So you guys, the most liked comment said that there was no way to tell if a reaction is oxidation reduction. So we'll go through a couple oxidation reduction reactions, and then we'll look at the last two questions, okay? So oxidation reduction reactions are happening when there is a transfer of electrons, okay? So how do you know, okay? Well, we'll kind of get there in a minute. But first of all, we got to remember that oxidation means you have the compound has lost an electron or atom, and then reduction is a gain of electrons. And if you watch the video, there was some different kind of things used so you can remember that. Oil rig is a common one. Oil stands for oxidation is loss. Again, and rig is reduction is gain. And these are in regards to electrons. So loss of electrons, gain of electrons. Or Leo the lion says grr. So Leo, loss of electrons is oxidation, and grr is gain of electrons is reduction. Okay, so again, you don't have to use those, but if they help, please do. So something like this equation here, we want to see what's kind of happening on the left side of the arrow and the right side of the arrow. Okay, so I see I can have the zinc solid. There's no charge on it. Okay, it's 0. That, and if there's no charge, that means the number of protons and the number of the number of protons and number of electrons are equal. Okay. I see my H plus, it has a positive charge, and I see this 2Cl minus. That's all on the left side of the arrow. Let's see what happened on the right side. Okay, so I got my H2. There's no longer a plus charge on it. So remember, this plus charge tells me there's one more proton than there are electrons. Now on the right side of the arrow, it's neutral. That means the protons and electrons are equal, okay? My zinc is now 2 plus, when before it was neutral. There was no charge on it. So here on the left side, the zinc had protons and electrons equal to each other. Here, there's 2 more protons. Remember, protons are positively charged. So there is a 2 plus charge on the zinc. What happened to my chlorine? 2Cl minus, 2Cl minus. Nothing's happening there with the chlorine. It kind of remained the same. So we can rewrite this equation and get rid of the chlorine to just focus on what changed. We can also break this reaction down further into these half reactions. This half reaction here with the zinc is only looking at what happened to the zinc. So the zinc went from neutral, or we can call that 0, to 2 plus, okay? So remember, on the left side, it had the same number of protons and electrons. On the right side, there are 2 more protons. That must mean it lost 2 electrons. And if it lost 2 electrons, that means the zinc was oxidized, okay? If I look at the 2H plus, on the left side, it was positive, so it had 1 more proton. And on the right side, it's neutral, okay? Now to keep the balanced equation, again, there's 2 H pluses, so there's 2 positive charges, and each one gains an electron, okay? And again, if you gain an electron, that is reduction. Okay. So this is in like an inorganic example, okay, where metals are involved. And I feel like it's pretty straightforward here. Remember, even though we're talking about like, protons and electrons must have been equal on the left side. And to get to 2 plus, that means we have 2 more protons. We can't think of it as like we gain protons, because remember, that would change the identity of the atom. The number of protons defines what element we're dealing with. So it's not the number of protons that changed, it's the number of electrons that change, okay, in these redox reactions, okay? So that's an inorganic example. Then we get to these organic examples, and it can be a little bit harder to tell. So these are some other ways to think of oxidation. You can think of it as a loss of electrons, like we said in our previous slide. You can think of it as a gain of oxygen or a loss of hydrogen. And if you just remember these for oxidation, you just know that for reduction, it's all the opposite. And I can always remember that oxidation is a gain of oxygen, because it's like I'm oxidizing it. It's getting oxidized. It's like getting oxygen. And I just know hydrogen is the opposite of oxygen. So if I'm gaining, if a gain of oxygen means oxidation, then a loss of hydrogen must mean oxidation as well. And again, I do use all these definitions because it just depends what equation I'm looking at to pull which definition helps me the best. So therefore, again, reduction is just the opposite of all these. Reduction is a gain of electrons or a loss of oxygen or a gain of hydrogen, okay? And so indicate which atoms in the reactants become oxidized and which become reduced, okay? And so let's look at this. So an A, it's not as straightforward with that zinc we had in the previous slide, because the zinc went from a neutral charge to a 2 plus charge, okay? And so here we have this C2H2, and we can see, and then we have our oxygen, and now we have CO2 and H2O, okay? So we can see that the carbon gained an oxygen, okay? So can you see that the carbon, it had no oxygen here, and now it has oxygen. So that is considered an oxidation, okay? The oxygen over here, right, it gained a hydrogen. So remember, gain of hydrogen is a reduction. So in this case, the carbon got oxidized and the oxygen got reduced. Okay, so then let's look at B. So we have the CH2O plus H2O. And this becomes CH4O, okay? So this one's a little trickier, right? But here we have a carbon with 2 hydrogens and an oxygen. Now we have a carbon with 4 hydrogens and an oxygen. So that's a gain of hydrogen. So again, the carbon gained hydrogen. So the carbon underwent a reduction. The carbon got reduced, okay? And if something gets reduced, something always has to get oxidized. They must go together, okay? So the hydrogen was kind of by itself here. Now the hydrogen ends up, with these oxygens. So we can say the hydrogen had a gain of oxygen and it got oxidized, okay? Let's look at this last example. This is the zinc oxide plus carbon. So we can see that zinc oxide had an oxygen and now it doesn't. So that's a loss of oxygen. So that comes under our reduction definition. The carbon had no oxygen, but it gained it. So a gain of oxygen is an oxidation. So zinc gets reduced, the carbon gets oxidized. Okay. So that's kind of a brief look at oxidation reduction reactions. So again, we came to this question of, well, how do we even know if it is a redox reaction? So you got to look at it and try to determine, is there a transfer of electrons here? Okay. And I said normally, if there's an ionic compound, right, meaning metal and a non-metal, like right here with this aluminum chloride, aluminum's a metal, chloride's a non-metal, and it's reacting with another metal that's neutral, this is usually a redox. Why? Because remember in our ionic compounds that these chlorides, each one has a 1- charge, and there's 3 of them. So that means our aluminum's at 3+. So on this side of the equation, on the left side, the aluminum's at 3+. And then it just goes to solid aluminum by itself. So that's at 0. So it went from 3+ to 0. So over here, it had 3 more protons than it did electrons. And over here, it has an equal number of protons and an electron. So it must have gained 3 electrons. A gain of electrons is reduction. Something must get reduced though, okay? The magnesium was neutral. Now it's involved in this ionic magnesium chloride compound. Again, each chloride is a -1, 1-, so that's 2- charges. So our magnesium must be 2+. So it went from 0 to 2+. That means protons and electrons were equal on the left side, but now there's 2 more protons, so it must have lost 2 electrons, okay? And so it got oxidized because a loss of electrons is oxidation. So this is a redox. So that's redox is a short way to say oxidation reduction reaction, or reduction oxidation reaction. So yes, this is a redox reaction. And then, is this a redox reaction? So this one can be a little bit hard, okay, because you might be saying, well, the hydrogen didn't have, well, I guess it has oxygen here. You might start thinking along that route, but what I'm really expecting you to do in this class is to recognize NaOH, and again, like that, like quick. You're saying NaOH, strong base, HCl, strong acid. Like those should be just kind of given. Those should be taped somewhere on your wall, maybe, you know, in your bathroom, wherever. You just need to you need to know what the strong acids and strong bases are. So when you see strong acid and strong base, hopefully you're like, no, of course that's not a redox. You know, this is an acid-base reaction, not a redox. I can even see they formed water and a salt. So no, this is not a redox reaction, okay? And that's it. All right, I hope you guys are well. Again, please join me in office hours. Remember, Dr. Farmer also has office hours. Dr. Sherritt also has office hours. There's tutoring from the Lark Center. And also there's Mesa tutoring where you can set up an appointment. They also have drop-in tutoring as well. Okay, I hope you are all safe and healthy. And please email me with any questions you may have.